Hello. In this lesson we're going to talk about equations of planes. Of course, everything that we're going to talk about in this lesson is going to take place in 3 space, because it would defeat the purpose to analyze planes into a 2 space, into a planar Cartesian system. Before we actually look at the several ways in which we can express the equation of a plane, let's think for a moment, what is the minimum information to uniquely define a plane, just like we did for lines? So if I have one single point, I can have a plane that contains this point, but it can rotate anywhere. So it's not enough. If I have 2 points, I can still rotate the plane along the line that goes through those 2 points. So still an infinity of planes, so it's still not good enough. The only way we can uniquely define a plane using only points is by having 3 points, with a condition that these 3 points are non-collinear. Because again, if they are on the same line, it makes no difference how many points you're going to take. But the minimum amount of points that you want to use is at least 3 non-collinear points. But we can also use directions, just like before. So I'm going to take at least 1 point for the position, and then let's see, if I take 1 vector, I can keep this plane from rotating anywhere, but I can still rotate the plane along the direction of this vector. So again, not good enough. I'm going to need a second vector. Obviously a vector that is non-parallel, because I can translate it, if it's parallel, and make it collinear with this first vector, and I defeat the purpose of having a second vector. So I have to have 2 non-parallel vectors and a point. I always need a point because the vectors don't give me any position, they only give me directions. So I can translate them anywhere I want. But if I have a point, I can state that the plane has to contain this particular point. And the direction is given by those 2 non-parallel vectors. Okay, so if that's clear, let's actually sketch on a Cartesian system what I just said. I'm going to try to express the equation of a plane using vectors. As I mentioned, I'm going to need a point, the known point P0, and I attach to it the position vector R0. And then, like I mentioned, I need 2 more vectors. I have this vector A and B. They are non-collinear, and I place them right at that point for convenience. What we need next is to create some sort of a relation between this point, or its position vector to be more precise, and these 2 direction vectors. So we can create some sort of an equation that we can express the rest of the points contained into this unique plane. Just like before, I'm going to take another point P that is going to be contained in this plane, and its associated position vector, because I can express this R vector as a sum between R0 and this red vector. But this red vector is what I'm going to express in regards to those direction vectors A and B. So for that reason, I'm going to construct another triangle here, which is formed by the scalar multiple of A and B. As you can see, I can create this linear vector with B, which is going to be a scalar multiple of B, SB, and a scalar multiple of A, which we're going to call TA, just so we can define this red vector as a sum of TA plus SB. As you can notice, it's a geometric addition of vectors. This is basically a plane defined by 1 point and 2 non-parallel vectors. So let's write down the equations that we can define based on our diagram. You can see how vector R is the resultant of the sum between R0 plus this red vector, which I'm going to reflect by using red parentheses. What is in the red parentheses is the resultant of the sum between the vector SB and the vector TA. Or let me just organize it properly and write it in one color. So it's going to be R0 plus TA plus SB. As I mentioned before, this position vector R with components x, y, and z, it represents the position vector for any point on that plane. The position vector R0 with components x0, y0, z0 is the position vector for a known point on the plane, because we need at least one point. This is the position vector pointing to that known point. And then we have the two direction vectors, A with the components A1, A2, A3, and B with components B1, B2, B3. The two non-parallel direction vectors parallel to the plane. You also see that we use two scalars, t and s, which are real numbers. So basically, the first type of equation that we can use to define a plane is the vector equation. In geometric format, it's going to look such as this: r equal r0 plus ta plus sb, while in algebraic format, the vector equation of a plane is as follows: x, y, z equals to x0, y0, z0 plus t a1, a2, a3 plus s b1, b2, b3. These are your vector equations for a plane. So now from this vector equation, it's very obvious, especially since you've seen the same thing for the equation of a line. Let's define the parametric equations of a plane. So they are as follows: x equals x0 plus ta1 plus sb1, y equals y0 plus ta2 plus sb2, and z equals z0 plus ta3 plus sb3. And these are your parametric equations of a plane. Remember how in the 2 space we had another type of equation to describe a line: ax plus by plus c equals 0. It was the form of it, and it's called the scalar equation of a line. And on a Cartesian system, since we work with planes, let's create the z-axis as well, which points towards us. If I add a z component to this equation, that's going to result into, depending on what values you take for this z value, if it's 0, it's going to be exactly that line L1. But if I take any other value, if I take increasing values for z, well, I'm going to determine a new line that's going to be parallel to L1 along the z-axis, and for any new value that you give to z, you're going to create a new line, as I sketch here, parallel to L1 and going along the z-axis. This scalar equation that you see here with x, y, and z components is basically describing all these lines that are parallel to that L1 that we had initially. So the equation doesn't describe just a line, but a multitude of lines. As a matter of fact, an infinity of lines. And an infinity of parallel lines basically is nothing else than a plane. That's why this scalar equation in 3 space defines a plane, not just a line. Now that we have this scalar equation of a plane, remember how the scalar equation of a line helps us find the normal vector to that line by creating the vector with the components a and b. The same way, the normal vector to the plane is going to be the position vector with the components a, b, and c. So basically, in addition to what I told you in the beginning of this lesson, you can also uniquely define a plane with only one point and this normal vector, instead of using two non-parallel vectors. So let me actually show you how that works out. So basically, you're going to have a plane, and on this plane, I'm going to take a point P0 with the coordinates x0, y0, z0. That's a known point. Well, a normal vector is going to be one that is perpendicular to the plane, so this vector n, and use the same letters for the components a, b, and c. If I take another point on this plane, a point P with coordinates x, y, and z, so any other point on the plane, basically the normal vector is going to be perpendicular to this vector as well, because it's contained in the plane. So the normal vector is perpendicular to any vector on this plane, by definition. First things first, let's express this vector P0P in an algebraic form. As we know from the lesson about expressing Cartesian vectors, it's going to be the difference between the position vectors that point to those 2 points. In other words, x, y, z minus x0, y0, z0. So the vector P0P is x minus x0, y minus y0, and z minus z0. That's just to define this vector in an algebraic format. And now, since the condition is that n is perpendicular on P0P. That also means that the dot product between n and this vector P0P is going to be 0. We're going to verify that by just performing the dot product between these two vectors in an algebraic format. So instead of n, I'm going to write its components a, b, and c, and the same for P0P. And that has to be 0. So let's perform the operation and see what we obtain. Remember the definition of the dot product. We're going to multiply the x components plus the product between the y components plus the product of the z components. One thing I like you to notice about this is that a, b, and c and x0, y0, and z0 are going to be numeric values. They are constants. Only x, y, and z are variables. So in the next step, I'm going to group these variables in the front and all the scalars at the end, because it's just going to be a numeric value. As I just said, what I have in the parentheses here are just constants, so I can denote all that expression with a d. It's going to be a scalar. I'm going to rewrite all this expression once again in the simplest form possible, so it's going to be ax plus by plus cz plus d equals 0. And that's exactly what I told you earlier, it's the scalar equation. But this is the scalar equation when we started with a vector n that was perpendicular to the plane and had the components a, b, and c. That's a normal vector to the plane. I hope this makes it clear why we can use those components a, b, and c to define the normal vector to the plane. Obviously, any other vector parallel to the normal vector, like this vector n1, is going to be also a normal vector to that plane. These vectors are not unique. That's what you have to understand. As long as they are scalar multiple of each other, they are parallel vectors. So they can be placed anywhere you wish, but they have the same direction, so they are perpendicular to the plane. Also, any point, like for example this P1, I'm taking here with coordinates x1, y1, and z1, is going to be a point on the plane if these coordinates x1, y1, and z1 satisfy the scalar equation of the plane. So if this expression ax1 plus by1 plus cz1 plus d equals 0 indeed, then the point is on the plane. Just to review in short, we have three types of equations that we can use to express a plane: the vector equation, the parametric equations, and the scalar equation. And with this, I'm concluding this lesson. Thanks for watching.